packaged. The following simplified sequence shows how masks are used to build transistors step by step. The first mask creates a well of doping so that the neighboring N-type and P-type substrates exist on the same wafer. The P and N channel regions are specified and electrically isolated by the growth of silicon dioxide. Next, the gate electrodes, which turn the transistors on and off, are formed. Masks number 4 and 5 define the source and drain regions of the N-channel and P-channel transistors. The next mask defines the contact holes, which will enable the aluminum wiring used to interconnect the individual transistors to contact the source, drain, and gate region of each transistor. Most integrated circuits use from 12 to 25 masks, depending on the complexity of the circuit and the type of process. And now, let's go into a research laboratory and follow a very simplified version of a CMOS fabrication process. From start to finish, a complex process may involve hundreds of individual operations and may take a number of weeks to complete. To have a successful run, control of contamination is extremely important. It takes just a few microscopic dust particles to drastically reduce the yield of effective semiconductor devices. The equipment, gases, and chemicals that come in contact with the silicon wafers must also be of the highest purity and free of contamination. To start CMOS fabrication, P-type wafers with a specific resistance are selected. All types of integrated circuits, including CMOS, are fabricated using 4 basic techniques: formation of thin layers of silicon dioxide, introduction of dopant atoms, deposition of a variety of insulating and conductive materials, and precision patterning of each of these layers. Before the process begins, the laser-scribed identification number of each wafer is recorded. We start by cleaning the wafers in hot acids. Hydrochloric acid, sulfuric acid, hydrogen peroxide, ammonium hydroxide. That's what it takes to remove all the organic and metal contaminants. This cleaning procedure is repeated throughout the process to make sure the surface of the wafers stay absolutely clean. The wafers are rinsed in deionized water and spun dry in filtered nitrogen gas. In a vertical furnace, high temperatures will be used to grow a layer of silicon dioxide. Silicon dioxide is a glass-like insulator which protects the silicon substrate beneath it from unwanted reactions. Pure oxygen reacts with the silicon surface in a hot furnace to grow a thin layer of silicon dioxide. This process is similar to the way the sun's heat and the air's oxygen turn the shiny new paint job of a car to a dull coat over the years. The silicon dioxide layer will be etched and used as a stencil to dope specific regions of the wafer. But first, the pattern for the stencil is applied to the silicon dioxide through a photographic technique called photolithography. The first mask pattern will be transferred onto the wafer using photoresist, a material which is sensitive to light. In slow motion, we can see the thick photoresist, which is a resin dissolved in solvents, evenly spread over the surface. The wafers transfer to heating plates and bake at low temperatures to evaporate the solvents, leaving a thin layer of resist. The wafer then enters a computer-controlled machine called a stepper. Inside, the wafer is positioned underneath the selected mask pattern. Ultraviolet light exposes the pattern across the surface of the wafer. In this way, many chips are made on a single wafer. By increasing the diameter of the original crystal, larger wafers are sliced and more chips can be made on each wafer. The wafers are then developed. There are two types of photoresist, negative and positive. A negative resist hardens when exposed to light and remains on the wafer when developed. In this run, a positive resist is used. When exposed to light, the resist changes chemically and is removed when developed. The regions of silicon dioxide, now unprotected by photoresist, are then etched. Although acids can be used for etching, most wet chemicals etch in all directions at equal rates, which can result in undercutting of the photoresist. Undercutting could create an inexact transfer of the mask. When a critical fine etch is needed, the wafers undergo a dry etching process called plasma etching. In the plasma chamber, a chemically reactive gas provides free fluorine atoms, which react with the exposed silicon dioxide to leave sharp vertical walls. High magnification SEM photographs show the precision of these etched regions.